So I often say that big data need not be random. In fact, it could be completely deterministic. However, it can, and like all data sets, contain noise, and often does, and it could even be completely stochastic. And so we're going to look at an example of that by looking at a model of user preference. So we're going to look at a binary classifier problem where there are two classes, positives and negatives, and I usually use black and green for that. But I'm going to use gray and green so it's easier to see my visualizations. So when you see gray, think black, and be glad it's not all black. So, for example, we may have gray fast food versus healthy green food, or a gray business attire versus a green fun spring attire, or something like that. Now, the key here is that some people prefer gray and some prefer green. And what we mean by prefer is they express a preference by choosing one more often than the other. So they probably will do both at some point in time, but they like one more than the other. And we're going to model this scenario using a little simulation I call My Favorite Die. So we're going to do a random experiment, 1,000 trials. X sub I is going to be the outcome of the ith trial. And each trial is going to be of the following. Randomly choose a 6-sided fair die or an 8-sided fair die. Now, the 6-sided is the green, the 8-sided is the gray. So, the negatives for green, the positives for gray. Choose one at least twice as often as the other. That's very important. The one you choose most often is your favorite. In other words, that's your preference. Although you'll be using both, you'll prefer one to the other. Roll the chosen die, record the result. 1 to 6 for the 6-sided die, 0 to 7 for the 8-sided die. This way they both have the same expected value. So what if you like the green one? Well, you roll the green die, and we get an observation. And so the first user likes the green, so they roll the green, and they might roll it again. And once again, we get a number. And notice that both of these numbers you could have gotten either with the gray or the green. So if they roll the gray and get a number, then that number, which is a 5, is the same number that we got in the first roll. So this means the first person uses the 6-sided green die twice as often as the 8-sided. But we've got to figure out that for ourselves. All we see are the numbers, not the colors of the dice that they used. So if we're doing this for 1,000 trials, she likes the green one. So that means that in this 1,000 trials, the green one shows up twice as often. At least twice as often. Now, the second observer might be the person who likes the gray one. So they roll the gray die and record their observations for 1,000 trials. Notice that sometimes you'll get a 0, which you cannot get with the green die. But everybody's going to use both die at times, so they're both going to sometimes get zeros. So there's two distinct classes in this data. Those who prefer green and those who prefer gray. Now, each trial is a random choice, and subsequently it's independent of every other trial. So suppose we have our observations. Notice all we have is the numbers. So in observation 2, was it the 6-sided die or the 8-sided die that was their favorite? What about in observation 14? Did they favor the 6-sided die or the 8-sided die? Well, actually, the answer is quite easy. All we have to do is a little probability. So let capital X be associated with the use of the 6-sided fair die. Let capital Y be associated with the use of the 8-sided fair die. We have two classes. Class 0 uses X twice as often as Y, at least. Class 1 uses Y twice as often as X, at least. So notice we have two random variables here, and Class 0 prefers one over the other. Class 1 prefers the other over the X. So let's look at the averages. So if we look at the X having numerical outcomes x1 up to xm, then if we rolled a fair die where X is in S equals 1, 2, 3, 4, 5, 6, then x1 is 1, x2 is 2, so on and so forth, then the average is just the sum over the outcomes of X times the probability of X, or equivalently the sum, j equals 1 to capital M, of X sub j, P of X sub j. For the 6-sided die, this all the probabilities are the same. So the X goes from 1 up to 6. So we get 1 plus 1 6 plus 2 6 plus 3 6 plus 4 6 plus 5 6 plus 6 6. And that's 3.5. For the 8-sided, notice that Y here is our variable for the 8-sided die. We get 3.5. Why? I started with 0 and ended with 7 because I wanted the two scenarios to both have the same average. So if mu is the mean, or the average or the expectation, then the variance is the expectation of the quantity x minus mu squared for the variable x. Now, what this means is that we're looking at the means. The mean is the same for both the x and the y. What's going to be different is the spread. So for the 6-sided die, the variance, we look at this expected value where we're dividing by 6 and taking 1 minus 3.5 squared, 2 minus 3.5 quantity squared, so on and so forth. And we get a variance of 2.91. For the 8-sided die, we get a variance of 5.25. And variance is a measure of spread. So if the variance of x is less than the variance of y, then that means y is more spread out than x. And that's exactly what characterizes this problem. The 8-sided die has more variance than the 6-sided one. And variance yields our answer. So for the class 1 variance, or let's do class 0. So the variance for class 0 should be less than the variance for class 1 because class 0 uses the lower variance die more often than the higher variance die. In fact, twice as often. So the variance of class 0 should be 2/3 of the variance of x plus 1/3 of the variance of y, which is 3.69. And that's the upper bound for the variance. So if we get a variance less than 3.69, they must be using the lower variance die, the green one, more often than the gray one. And therefore their preference is for the green. Likewise, if y is used twice as often as x at least, then we get 1/3 the variance of x plus 2/3 the variance of y, and that's 4.47. So if the variance is larger than 4.47, we know that their preference is for the gray. So if we look at observation 2, it turns out that the variance is 3.6. We hadn't looked at that yet. So just to summarize, if they prefer the green, their variance will be less than 3.69. If they prefer the gray, their variance will be greater than 4.47. So the variance for this first one was 3.688. So in observation 2, they favor the green one, the 6-sided die. In observation 14, their variance was 4.496. So they favored the 8-sided die. And it gets even better. So one of the nice things about random processes is the law of large numbers. We can get empirical averages to approach theoretical expectations as we simply let the number of trials go to infinity. So that means for an arbitrarily large n, the variance will approach exactly 3.6944 or smaller. And similarly for class 1. The more data we have, the better the results. This is true in general with random phenomena. More data implies